The chemical reactions that we've looked at up until this point are what we call molecular equations. They show the chemicals, even though they're put into water, they show them as the molecules or the formula units. So everything is combined into the formulas. This is not the whole story though. When a material is put into water and it dissolves, a more informative way of looking at these reactions is what we call the complete ionic equation. So our aqueous, strong electrolytes are written as ions because that is how they exist in the solution. So if it's a soluble salt, we break it apart into the ions. If it's a strong acid, we break it apart into the ions, or a strong base. If something is insoluble, like a weak electrolyte or non-electrolytes, they're written in the molecule form. So these would be things like solids, liquids, and gases. They stay as the molecule, or if it's an insoluble salt or weak electrolyte. So our example written above, anything that says AQ gets broken into the ions. So notice our potassium hydroxide now becomes potassium and hydroxide. The magnesium nitrate gets broken into the ions, and the potassium nitrate on the product side is also broken into the ions. Our magnesium hydroxide, because it forms a solid, gets left as the formula. So if it's a solid, a liquid, or a gas, it stays as the formula. So ions that are both in the product side and the reactant side are what we call spectator ions. Essentially, they're watching the reaction happening, but not participating, kind of like a spectator at a sporting event. So in our example here, which would be the spectator ions? It's the potassium and the nitrate. It is present in both sides of the chemical reaction. So these would be the spectator ions. They're not participating in the chemical reaction, but they are present. If we want to write an equation that shows exactly what is happening in our chemical reaction, we would write what's called a net ionic equation. The spectator ions are not participating, so we do not need to include them in our final net ionic equation. We only include the ions that form the solids, liquids, or gases. So essentially we're canceling out like terms from both sides of the reaction and writing what is left. Here's one for you to practice. See if you can write the ionic and the net ionic equation for each reaction. Pause the video and determine the reactions. If we look at our chemical reactions, we've split apart anything that says aqueous. So the 2 that was the subscript in our potassium sulfate becomes a coefficient because it tells us that there are 2 potassiums. Our sulfate stays as one entire unit because it's a polyatomic ion. It does not get split apart. The coefficient in front of silver nitrate goes both for the silver and for the nitrate. On the product side, because we have potassium nitrate that is aqueous, that gets split apart into the ions, and the coefficient gets used for each of the ions. The silver sulfate, because it's a solid, does not get split into ions. It remains the entire compound. To cancel our spectator ions, we have potassium on both sides of the reaction. We also have nitrate on both sides of the reaction. So those are going to be our spectator ions and don't get written in our final net ionic equation. The silver and the sulfate become silver 1 sulfate. And this is our net ionic equation. If we look at our sodium carbonate, again, containing reaction, we are going to split it apart into each of the ions. So sodium carbonate, the 2 for the sodium becomes a 2 in front of the sodium ion, telling us that we have 2 of them. Got carbonate, 2 HCl, we've got 2 in front of the H+, 2 in front of the Cl-. This produces 2 sodium chloride, and again that 2 goes for the sodium and also the chloride. And the reason we split this apart is because it is aqueous. The carbon dioxide, because it's a gas, does not get split apart, so it remains as the molecule, as well as the water because it is a liquid. So overall, our net ionic equation are the carbonate ions and the acid or the H+ ions forming carbon dioxide and water in our net ionic equation. Now this reaction might look familiar. It's one that we looked at in lab. Acid-base reactions are a special type of chemical reaction. They can also be called neutralization reactions because the acid and the base properties neutralize each other to form water. Here's an example. We know it's an acid-base reaction because it starts with H, and so we've got nitric acid. Our bases contain hydroxide at this point in time. We will expand this definition in the future, but at this time, an acid is going to have H+, a base is going to have OH-. The net ionic equation, no matter what the acid-base reaction is always H+ plus OH- gives us water. The H+ is from the acid, the OH- is from the base, and when they react, they give us liquid water. And this is if the salt that is performed, salt is a generic way of saying ionic compound. So if that salt that is formed is soluble, our overall net ionic equation is always the H+ plus OH- gives us water. I do want to note that chemists frequently will write H+ as H3O+, so this is just the H+ plus water, and that forms H3O+, which is also known as the hydronium ion. So these get used, H+ and H3O+ get used interchangeably. There are lots of common acids. So they get used for lots of different things like explosives and fertilizers. Hydrochloric acid, this is one that's near and dear to you, whether you realize it or not. This is the acid in your stomach that helps to break down your food. And so the concentration in your stomach is about 0.1 molar, which is a pretty common concentration for using in the lab. You'll notice there is a range of strengths. So the strengths increase as we go up this table. And we'll learn more about the strengths of acids, but remember, strong acids dissociate nearly 100%. Weak acids, most of it stays as the molecule. Also a list of common bases. Notice nearly all of these have OH minus. They get used for a range of uses, okay, like making soaps or cement. Sodium bicarbonate, that's baking soda. It gets used for making food, cooking. We also have some that get used as antacids. So antacids are just like it sounds. It's anti-acid. So we have to add a base in order to neutralize the acid in your stomach. So our baking soda and also our ammonia, those do not have OH minus. If you continue on into the next semester chemistry, you'll learn why those are also considered bases. But ammonium hydroxide is technically what ammonia is when it's dissolved in water. Because if we have our NH3 plus water, we get NH4 plus OH minus. And so ammonia and ammonium hydroxide get used interchangeably in the chemistry lab. See if you can write the molecular ionic and net ionic equation for the reaction of aqueous nitric acid and aqueous calcium hydroxide. Pause the video and determine the reactions. Let's start with nitric acid. So nitric acid, if it's an acid, it's H plus is our cation. And nitric, doesn't say hydro, so we know it's a polyatomic ion. So nitric is the nitrate ion. They have a +1 charge and a -1 charge, so it just takes one of each. If we look at our calcium hydroxide, calcium is a +2 charge based on its position on the periodic table. Hydroxide is an OH minus, so it's going to take 2 hydroxides to balance the charge of the calcium. So when we've split these into the ions, we're going to get H plus dissolved in the solution. We're going to get nitrate dissolved in the solution, get calcium, and hydroxide. Now when we predict the products, we're going to take the cation of one and put it with the anion of the other. So the H plus and the OH minus are going to combine, and when H plus and OH minus combine, we get water. We're going to take the calcium and the nitrate, and we're going to form calcium nitrate. Nitrate's a -1, calcium's a +1. So we're going to need 2 nitrates to balance the charge of the calcium. Now to balance our chemical reaction. So we see we have 2 nitrates in our calcium nitrate, so we're going to have to put a 2 in front of our nitric acid. So we've got 2 nitrates on the left side. 1 calcium on each side, so we're in good shape there. We've got 2 hydrogen and 2 hydroxide, so to balance that, we need a 2 in front of our water. balance our equation down, our net ionic equation, which we've been writing. We're going to need a 2 in front of our H plus and in front of the nitrate. We need a 2 in front of the hydroxide because of the subscript. 2 waters and 2 nitrates. So now this equation here is our complete ionic equation. We have our molecular equation. We have our complete ionic equation. Now if we want to write our net ionic equation, we need to cancel ions that are the same on both sides. So if we look, we have 2 nitrates on the left side, 2 nitrates on the right side, so we could cancel those out. We've got we've got 1 calcium which is a 2+, 1 calcium, cancel those out. So what we're left with is almost our net ionic equation. However, this can be reduced because we have a 2 in front of each of a coefficient of 2 in front of each compound, so we're just going to reduce it. And we get H plus OH minus gives us water, which for acid-base reactions, this is what we would expect. Here's a practice for you. Predict the products, balance the equation, write your net ionic equation. So for the products, we're going to take the cation, combine it with the anion. So in this case, we're going to get water. H plus and OH minus gives us water, which is a liquid. We're going to take the barium and combine it with the chloride. Barium is a +2, chloride's a -1. And so we get barium chloride. Now to balance this reaction, we've got 2 chlorides, so we're going to need a 2 in front of our HCl. This gives us 2 H's and 2 OH's. So if we put a 2 in front of the water, that balances our chemical reaction. If we want to write the complete ionic equation, we break it up into the ions. For each of the aqueous solutions, the subscripts become the coefficients. Anything that is solid, liquid, or gas, like our water, remains as the compound. And if we have aqueous, that gets split into ions. And so our complete ionic equation would look like this. If we want to write the net ionic equation, we cancel ions that are the same on both sides, which are barium and chloride. And again, because this is an acid-base reaction, we know it's acid-base because it's H plus OH minus. We get a net ionic equation of H plus OH minus gives us water, because we can reduce this. There's 2's in front of each one, so we can reduce it to H plus OH minus yields water.